Hi, my name's Liz Rice. I am Chief Open Source Officer at Isovalent, which is the company behind the Cilium networking project. And I'm also the chair of the Technical Oversight Committee at the Cloud Native Computing Foundation. I'm going to talk today about a technology called eBPF, which is something that I've been really excited about for a few years now. And I'm going to talk about the way that it's enabling new tools for enforcing developer intent with regard to security. So before I talk about what eBPF is, let's just briefly touch on this idea of developer intent. As a developer of an application, it stands to reason that if you're working on a particular component, you know what that component is supposed to do. And by extension, what it's not supposed to do. If we're using a microservices architecture, this can be really quite straightforward to reason about. For example, if you're working on a product search service for an e-commerce app, you would expect that search service to connect to a product database, but you wouldn't expect it to connect to a payment gateway, and you certainly wouldn't expect it to be running a cryptocurrency mining executable. With shift left, we want to encode this knowledge of developer intent into runtime policies so that developers are becoming more responsible for the security of the application they're working on. And this isn't new. We've had runtime policy tools for many years. For enforcing runtime executables, we've had things like seccomp and AppArmor and SE Linux. And we've also got networking policies in Kubernetes and service mesh, and before that, firewall rules. But traditionally, these tools have been pretty hard to use. It's been pretty hard to write the policies for these tools. Taking a couple of examples, the default seccomp profile for Docker is well over 700 lines of JSON. It's a really good default definition, but in my experience, most organizations don't have the time and resources to write and maintain a tailored profile for every different service. As another example, a few years ago, Jess Frizzell wrote a tool to help generate AppArmor profiles because, as she said, who would ever want to create one by hand? So if reviewing profiles is this painful, you can be sure this is not something that people are doing if they can possibly avoid it. One of the reasons why these are hard is because they require quite a detailed knowledge of what's going on at a Linux system level. For example, seccomp enforces what system calls are allowed. But when we're writing applications, most of us use languages that use much higher level abstractions. We don't really think about the underlying syscalls. So we really want policy enforcement that allows us to take our understanding of what an application is supposed to do, but at a level of abstraction that is familiar to us as developers. eBPF is a technology that's enabling a new generation of tools for networking, observability, and security. My prediction is that although most of you won't write much eBPF code yourselves, if any, a lot of you will find yourselves using eBPF-enabled tools that offer these higher level abstractions and give us much more usable security policy definitions. So what is eBPF? Well, it stands for Extended Berkeley Packet Filter. And I could talk about the history of why it's called that, but honestly, it's not terribly helpful. What's more important is what eBPF does. And that is, it makes the kernel programmable. You can write custom programs and have them run in the kernel without having to write a kernel module. You can load them into the kernel dynamically as you need them. Now, there's been a lot of work to develop this eBPF technology in the kernel and the associated tool chains and verifying technologies. And recently, an eBPF foundation was set up that allows collaboration on these eBPF features in operating system kernels. Isovalent has been deeply involved in this process. So, although I don't expect that many of you will write eBPF code, I think it's very helpful to get a mental model of what eBPF programs kind of look like. So, the eBPF code itself runs in the kernel, but it's put there, it's loaded into the kernel by an application running in user space. The eBPF program is triggered by some kind of event. The user space part will associate the program with an event. And there are lots of different types of event that can trigger these eBPF programs. For example, it could be a system call. It could be a network packet arriving. It could be that the kernel hits a particular trace point or a particular security event that's been added into the kernel. So when one of these events is hit, if there's an eBPF program associated with that event, it gets run. To make this a bit more concrete, here's a very simple example of a kind of hello world eBPF program that generates some trace. And in this example, it's attached to the execve system call, which is used to run new executables. So every time that execve system call is hit, because a new executable is running, that print message generates some trace. And as you can see from the output at the bottom of the screen, that trace includes some contextual information. The eBPF program is running in the context of the trigger that caused it to run, and it knows information about that context. For example, it knows what process ID and what executable name is being run. So you're unlikely to have to write code directly to run in the kernel, but modern eBPF-based tools can offer abstractions that hook into the kernel in this kind of way. So let's take a look at some examples of tools that offer custom policy checks that are using higher level abstractions, but that are actually implemented using eBPF. First example I want to show is a Falco rule. So Falco is a security tool. It has rules that are triggered by system calls. You could kind of think of them as a bit like seccomp on steroids. Falco converts the rule defined in text that you can read as a human being into eBPF code that will evaluate the condition. So in this example, I think it's pretty easy to see that in this example, the system call is open. And if the context of that open code shows that it's a process that isn't Skype or WebEx, but that it's trying to open a camera device at /dev/video0, then this rule is going to complain. Perhaps it's a suspicious event. Tracy is another eBPF security tool. And in this case, they use a policy language called Rego. You may have come across that before because it's used by Open Policy Agent. This example actually shows something a little bit more secure than checking system calls and their parameters, because there's actually a window of opportunity for an attacker to change the parameters of a syscall before it gets executed. There was a really great talk about this at DEF CON earlier this year. But in this example, Tracy's using a Linux kernel security checkpoint that allows looking at the name of an executable. And in this case, this rule is spotting if an executable is being run from memory rather than from disk, because that's potentially an indicator of malicious activity. So Rego, as used to define this rule, is getting more and more widespread, but it's nowhere near as widespread as YAML. Let's take a look at an example of network policy, which is defined in YAML. I mentioned before the example of a policy used for a product search service where we expect it to get requests from a front end, and it's only allowed to make requests to a product database. So that YAML policy makes sense. It's relatively easy to understand how that policy maps to the intention of the developer building this product search service. Turns out that's actually not sufficient because there are a few gotchas in Kubernetes network policies. And in Cilium, we developed a network policy editor to help visualize how these network policies work. So this is the visualization of a functional version of that policy for product search. And there are a couple of additions compared to what I showed in the previous slide. The important one is on the bottom right. If you want to use DNS for service discovery, which is what Kubernetes does, you have to explicitly allow for DNS requests in your network policy. Otherwise, your DNS requests will get dropped, and then product search will never be able to find that product database that it needs to talk to. Another optional addition that I've included here is on the bottom left, where I've allowed for any app labeled as a monitoring app in the cluster to be allowed to make requests to this service. A lot of organizations will require all the apps running on their cluster to be subject to organization-wide monitoring like this. Now, these kind of gotchas, things that can go wrong with network policies, can put people off from writing them. This is generally true when we have to write policy definitions. If they're hard to write, people will avoid doing it. But they are hugely powerful. So we wanted to make it as easy as possible to create and validate and check your network policies. So I do recommend you check out networkpolicy.io for more resources on how to successfully build Kubernetes network policies. So I've talked about some abstractions that make it easier to create these policies, but why on earth does it matter to you that these are implemented using eBPF? Why should you care? Let's take a look at what it means in the world of Kubernetes to be able to run custom code in the kernel. Our applications are running as containers, and those containers are inside pods. But there is only one kernel per host, whether that's a bare metal machine or a virtual machine. Every container on the same host shares the same kernel. Whenever an application that's running in a pod wants to do anything like read or write to a file or make a network request, or if Kubernetes wants to create new containers, all of these actions require assistance from the kernel. And the kernel is doing all of these operations for everything that's running in user space on that machine. So that means the kernel is aware of everything that's happening in all of the processes on that machine. And it has access to information about all of these processes that are stored in kernel data structures. So if we attach eBPF programs to the right events in the kernel, our eBPF custom code can be aware of all the interesting things that are happening too. And then we can write user space code that communicates with these eBPF programs and brings all that information together in ways that are really useful for observability and security. And we can do things like redirect or drop network packets from inside of eBPF. And that's the basis of Cilium networking. So importantly, we can add this instrumentation, whether it's for observability, security, or networking, without changing the application or the way that an application is configured. Typically in Kubernetes, we see a lot of instrumentation using a sidecar model, Nathan Leclerc put together this really nice cartoon about the Sidecar model. And let's dig into why the kernel and eBPF is a really interesting replacement for the Sidecar model. So when we instrument a pod using a Sidecar, we have a Sidecar container that sits within the pod, and it's aware of what's happening inside that pod and only inside that pod. To get that Sidecar container into the pod, we have to have some YAML. You probably don't write that YAML by hand. There's probably an automated process, perhaps in your CI/CD pipeline, perhaps at admission control, but there will be something that automatically adds the Sidecar container into the pod YAML definition. But what if that process goes wrong? What if you somehow manage to deploy an app without putting it through that process, without instrumenting it with the Sidecar container? If your pod is deployed without the Sidecar, then that pod is not instrumented. If an attacker manages to run something maliciously on your cluster, they almost certainly won't instrument it for you. So relying on sidecars relies on the ability to inject this YAML, whereas with eBPF, we don't need that. Because eBPF runs in the kernel and can be aware of all of the applications, we don't need to make any configuration changes at all to the application in order to be able to observe it and instrument it. So eBPF gives us this ability to create policy checking tools, and it gives us real in-depth visibility. So I want to show you something that we've been experimenting with, where Cilium is aware of the networking flows inside Kubernetes. We've also seen how eBPF can easily have the context for its trigger. So we know what process was running. If we look at a network connection, we can see what process was running, what pod it was in, what executable was running. We can see exactly what creates any network connection. In this example, my pod is quite legitimately talking to Twitter and an Elasticsearch service. But imagine one of those network connections is going to a cryptocurrency mining pool or some kind of command and control center. With this level of detail that we can obtain using eBPF, we have all the forensic information we might want to be able to see how that network connection was created and by exactly which executable in what pod. We can use that information to figure out whether the pod was compromised after it was deployed or before it was deployed at some point during the build process, perhaps. So all this detailed information gives us hugely powerful forensics. And I think this is really a summary of the power of eBPF. It's giving us real new tools. It's enabling the creation of really powerful tools for enabling networking, observability, and connectivity solutions across the world of cloud native. If you want to learn more about eBPF itself, the foundation website is at ebpf.io with tons of information. And of course, if you'd like to learn more about Cilium or what we do at Isovalent, do please come and have a chat in our Slack channel or just come and ask me questions. Thank you very much.